my voice as well.
I'll turn off the microphone. We are live and on the air, according to Google. Thanks, everybody, for joining us both here in North Carolina at the Triangle Bitcoin Meetup and all of you out there on the internet. We are very excited to have Muneeb Ali from BlockStack join us, especially at the late last-minute notice. It was very nice of you to pitch in and help out to fill in this void we had in our schedule. But we're definitely excited to learn about, re-decentralizing the internet and, your vision for how we can actually make the internet more like what it was probably originally intended to be. So without further ado, I'll hand it on over to you.
Cool, awesome. Well, thanks for having me. Let me just do the screen share. Cool. So I'm Muneeb from BlockStack. My background is basically distributed systems. I just wrapped up a PhD in distributed systems from Princeton. And along with my co-founder, Ryan Shea, and our core team, we've been working on BlockStack for 2 to 3 years now. A quick reminder that if you want to tweet at BlockStack, the handle is blockstack.org, and I'm at Muneeb on Twitter. So today, this talk is basically divided into 2 parts. The first is the motivation behind, what's wrong with the internet and why do we need a new internet, or why do we need to decentralize the internet. And then the second part is where we'll do a technical deep dive into how we are actually building that using BlockStack and what are the design decisions that we have made over the years and what were the reasons behind it. Right. So for most people sitting in the audience under 25, they probably wouldn't recognize this, but this was the Chrome of the 90s. This was the first browser, the Netscape Navigator, that came out in around 1994. And people my age, whenever they think of the good old days of the internet, they kind of like have a very strong emotional feeling of like late nights sitting in front of the Netscape browser. So if you look at what internet was back then, and you compare it to like what happened over time. So let's say you're sitting on your laptop or your desktop, and internet is like this like giant network that you connect to, and say you want to connect to Facebook. What most people don't realize is that just when they are trying to establish a connection to Facebook, there are all these different third parties in the middle. For example, at your meetup location, you're probably connected to some Wi-Fi device, and you would have a cable provider like Time Warner. And you're making queries to some DNS server that you don't even know where is that server. And you're kind of like trusting the results that that server is giving you. And then if you go to facebook.com and you see this like green lock sign that kind of like makes you feel secure, most people don't know that it's usually just one company, probably VeriSign in most cases, that is saying, hey, trust me, you're talking to the right Facebook, right? So, and ICANN is this nonprofit foundation that kind of like runs this core infrastructure, DNS, the domain name system, that everyone basically relies on. And that tells you where facebook.com is and what server you should be talking to. And then there are all these other components like CDNs, like Akamai would actually be delivering images for you for Facebook, and they can like change the content if they want, and people would basically just, they don't even think about it. So, and things do go wrong in this design. A recent example is in Turkey, the VeriSign of that country, Turk Trust, was basically issuing the wrong certificates for Google. So if you're sitting in Turkey at that time and you thought you're connecting to Google or Gmail, you could have been connected to the wrong Google and the wrong Gmail, and you wouldn't even know because you'll still see the green secure sign. So the first problem with the internet really is that we trust these third parties that we don't even know exist, right? So there's this concept of blind trust that we're forced to do that. The second thing that happened between the 90s and now is that the internet became more and more centralized. There are these like really big players in the middle, the Googles and Facebooks of the world, that most people basically rely on. And let's say you want to send your friend a message. Your friend first connects to Facebook, and you connect to Facebook, and then you're sending a message on Facebook servers, right? So these companies own all of our data, and our laptops are just screens. These dumb terminals almost, which connect to our data that lives with all these companies, right? So the second big problem with the internet is that there is no ownership. Big companies and not the users actually own all the data. So if we can do something about these two large issues, we can re-decentralize the web and give the power back to the users. And this is where blockchains come in, and they completely change the game. Right? So those of you in the audience who are not that familiar with blockchains, I'll just give a very quick, very high-level overview, and then move on. So blockchains really started with Bitcoin. You can think of that as like a payments application, but there's more to that. Like having a currency component for blockchains is actually very fundamental to the design of the technology itself. But you can think of this as like all these big banks and companies like Western Union are kind of like these centralized parties in the middle that Bitcoin is trying to replace, right? It's saying that, hey, if you want to send money to your friend, you don't have to go through Western Union. You can actually have a decentralized network that nobody owns and no one operates, and you can send your payment on the decentralized network, right? So this is what Bitcoin is doing, and I don't know if you have checked the price lately. Like the price is going up. People are excited that, hey, this technology or this revolution is actually happening. And for users like who understand the high-level concept that, okay, fine, we are removing the middlemen and removing these centralized companies from the picture and having a completely decentralized network, they just need to know like very basic things like what's a private key. A private key looks something like this, although users would never actually see it. They would be using it through some interface. And this private key is extremely secure. Like if someone cannot just randomly guess this number. You can think of this as like a very long and very secure password. And with this private key, you can actually own assets like Bitcoin, right? So the money that you own with your private key is yours. And there is no other party involved in that relationship. It's like owning an asset. So we looked at this technology and we started thinking that just like what Bitcoin is doing to banks, you can do that to these data banks on the internet. Facebook is really a data bank. It's sitting on all of your data, and we can enable an internet where, with a private key, you can actually own your username, or you can own your profile, or you could own all of the data associated with that profile. So this is the very high-level motivation for what a new internet could look like. And if you look at the timeline, the web, like Sir Tim Berners-Lee came up with the specifications around like late 89, 1990, and Netscape, the first browser, came out in around 94. And for blockchains, the Bitcoin blockchain started in 2009, and roughly in 2016, we came out with the first browser. It's still in developer alpha that lets you browse this decentralized internet that is secured by blockchains. This is what the browser looks like. So imagine that when you download it and you open the browser, you're not on the traditional internet anymore. Imagine that you're connected to a second internet or some like parallel universe, and this browser is your window to that universe. And you can, just like, in a normal browser, you can type in like CNN.com or Facebook.com, and the browser will resolve that and show you the content on CNN.com. Similarly, you can type in, let's say, Werner.id, right? So just like you have .com, .org, .net, we have top-level domains on this new internet. One is .id so it's a TLD for people. And this is Werner Vogels, the CTO of Amazon, and he basically registered his username and his profile on this new internet. And you type that in, and it resolves. And the really cool thing about this new internet is that all the data that you are actually seeing for Werner Vogels, there are cryptographic guarantees behind this data was actually written by Werner, right? So even if you want to change a single letter in his bio, you would have to either steal his private key and then make the change, or you would have to take down the Bitcoin network, right? Or the underlying blockchain that actually powers this internet. Right? So this is what the new internet looks like, that it just removes these companies and middlemen from the picture and replaces it with this decentralized open network. And now I'm going to basically go into how that is actually built. But at the high level, you can imagine that you can just register these domain names just like you would register muneebali.com on the normal internet, but on this new internet, you're registering it using private keys and using the blockchain technology, right? So you truly own that name. You truly own any data that you associate with it. And if you're an app developer, you can actually start building apps and register them, let's say, in a .app namespace, and that becomes like a app store, and people can publish their code. Other users can download these apps and start using it. And I'll discuss that in a little bit. So let's step back a little and like start taking a technical deep dive into how all of this actually works. All right. So the first thing is, I want to first talk about some design limitations. If you tell someone that, hey, why don't we just run the entire internet on top of blockchain, they would probably start laughing at you, because blockchains are like horrible for putting a lot of data in them or for running general purpose computing, right? Because every node that is actually participating in the network actually sees the blockchain data, or if there's any computation that needs to happen, if you send a transaction, every single node on the network needs to run that computation or that transaction, needs to process that transaction. So initially, saying something like, hey, let's just build the entire internet on top of blockchain sounds like a really, really bad idea, because blockchains are not really meant for that. They would not scale to that extent. And if you look at other traditional approaches for peer-to-peer networking, where users just like directly connect with each other, traditionally, in the last like 10 to 15 years, experience shows that these peer-to-peer networks give extremely horrible performance, right? Like you can imagine that, let's say, someone designs some sort of a data sharing network where I'm keeping user profiles on my friends' computers, and then my friend's computer goes down, and now no one can access my data anymore. Right? So this is a very simple example, but then there are actually very deep technical challenges with peer-to-peer networks, and why they break down at large scale, or how there are these problems like Sybil attacks that we don't have a good solution to, and so on and so forth. So by keeping these design limitations in mind, that, hey, peer-to-peer networks in generally don't really work, and blockchains are just horrible for scaling up and building large-scale systems using them. So keeping that in mind, now start thinking about communication channels. Let's say that it's you and your friend, and imagine that you have two types of communication channels between you, right? The red one is very high bandwidth, but it's not secure, right? And then there's a green communication channel. Like imagine almost like having two cards in your laptop, or one is connected to a network that is very low bandwidth, but it's extremely secure. That's the green channel, right? And that's kind of like what we are being presented with the current infrastructure. All the existing infrastructure for the internet is extremely high bandwidth, but it's completely insecure, just the way that the internet was originally designed. There's no concept of security there, like end-to-end security. And blockchains are extremely secure, but they cannot deliver a lot of data, right? So this leads to this separation of control plane and data plane, right? What we're really interested in is managing the control plane with the low bandwidth, highly secure channel, and then managing all of the data and scalability issues in the high bandwidth channel. This is almost like saying that you want to establish a secure connection between yourself and your friend. Even a piece of paper is kind of like a communication channel, right? You can write down your public key on a piece of paper, exchange it with your friend, like that's communication happening. And after that, you guys can just encrypt data and send it over the high bandwidth internet links. Will still be secure, right? So that green line is that piece of paper almost that you have, and blockchains kind of provide that. Right, so keeping that in mind, this is how BlockStack works. And what we are trying to build here is a replacement for DNS, the domain name system, which basically resolves things like CNN.com into an IP address, and also in replacement for the public key infrastructure, which is basically these security certificates that are associated with these names that basically tell you that you are connected to the right party. And also the data backends. Like imagine that the content for CNN.com is hosted somewhere, and then when someone goes to CNN.com, that is displayed in front of you, and you can actually see that content. So all the way, this is like completely from scratch, a replacement for all of this functionality that you have on the internet right now. So the first layer is the blockchain layer. And our design philosophy is that we should be able to use any blockchain. Like currently, we actually use the Bitcoin blockchain because it is by far the most secure blockchain out there. But the way we have designed the system is that you can run this on top of any blockchain, right? So we built this layer on top, which is called a virtual chain. Basically, what happens is that our software, if you're running a BlockStack node, you can send transactions which are embedded in Bitcoin transactions, right? So you're basically, let's say that you want to register a name. You're sending an operation saying name register, which is actually embedded inside a Bitcoin transaction and broadcasted on this low bandwidth network, right? Once that transaction goes through, all the BlockStack nodes would actually process that data, and they will be able to create a mapping that this domain name was registered by this public key. Right. There are actually more steps to that. We do that as a two-phase commit because we want to avoid a situation where someone sees your transaction, it's not confirmed yet, and they try to front run you and register that name. So we actually have a two-phase commit to make sure that nobody can front run you. So you first actually announce a hash of the name that you're trying to register. And once that transaction is confirmed, has like 6 to 10 confirmations, then you actually reveal what was the actual name that you're trying to register, right? So the interesting thing over here is that people who are running Bitcoin nodes, like Bitcoin now becomes a low-level layer, right? They would see these transactions, they would accept them as a valid Bitcoin transaction, but that transaction has no meaning for them, right? But people who are running the BlockStack nodes can actually process all these transactions in order, and they can actually build a global view of who registered what name, right? So almost imagine that every BlockStack node is building this local database of information, but they are not trusting anyone to construct that database because they're just processing the underlying blockchain and then constructing this view of, hey, this is what the ownership information looks like, right? So for each name that is registered, we also keep a hash of the zone file. Zone files are basically used in the domain name system. And so you can imagine that CNN.com would have a zone file that has all the information for what is the IP address, what are the MX records, which are used for like mail servers, and so on and so forth, right? And we use the exact same format for these zone files as DNS itself. I can actually quickly show you an example. So this is the zone file for Werner Vogel's, werner.id. It has a TTL, time to live. It has the IP address where his data is hosted. And given that he's the CTO of Amazon, obviously he's hosting his data on Amazon S3. If you resolve that, you'll see that this is actually a S3 endpoint. So coming back to the architecture, the next layer is the routing layer, which has the actual zone files. So remember I said that the blockchain is extremely bandwidth limited. You can't put a lot of data there. So we don't put even the zone file information in the blockchain, right? We only put the hash of the zone file in the blockchain. And we can fetch the zone files outside of the blockchain network, but then very quickly verify that we got the correct zone file, right? So going back to that example of the high bandwidth channel and the low bandwidth channel, what's basically happening is you're getting these zone files from the high bandwidth channel, but then you are quickly checking using the low bandwidth channel that did I get the correct information or not, and that works perfectly fine. So the next thing after the routing information, so the routing information is needed to basically find out where the content is, right, that I'm trying to resolve or trying to download. Like where is the website for CNN.com, right? Or where is the profile information for twitter.com/Muneeb, right? And so that's where the storage layer comes in. And whenever you look at storage, traditionally, whenever people want to decentralize storage, their approach is usually to have a peer-to-peer network. And I can go into more details on why we believe that that has a lot of problems. I mean, there are actually like a graveyard of failed P2P projects in the last decade or more. A lot of them ran into the same issues over and over again. Peer-to-peer networks are very hard to scale, and there are some known problems that in computer science we still don't have solutions to those problems. So what we are doing with our storage layer is something different. What we're saying is we can actually use existing cloud providers like Amazon S3, Dropbox, or Azure, but we can use them in a way that we are only putting encrypted data there, right? So the cloud provider has no visibility into what is being stored there. Secondly, we can actually replicate data across multiple providers, including your own servers. Like you can completely run your own Linux box, right? So we basically write drivers. So imagine that we treat them as like dumb hard drives. And just like if you buy a new hard drive and you want to plug it in, internally there's some disk driver that is used to mount that hard drive. So we treat them, we have reduced the Amazons and the Dropbox of the world to a dumb hard drive, right? We have written these drivers, and you can just plug any of these providers in, including a Linux box, right? So if you just want to run your own server, absolutely you can just run the Linux driver and use your own server as a data backend. Similarly, you can use BitTorrent or IPFS, whatever you want. But the main idea over here is that you can replicate data. Disk is cheap. You can just replicate your data across 3 or 4 providers and keep it encrypted, right? And that's the storage backend. And now you're not dependent on any single cloud provider. It's not like Dropbox would suddenly shut you down and your data would disappear. But you're also not dependent on some random strangers in the world who can just like shut down their laptop and suddenly your data would disappear as well. Right? So that makes the full stack. And all of this is actually implemented. You can check out github.com/BlockStack, and the main repository is BlockStack Core. which is the reference implementation for this protocol. And we have implemented all of this over the last many years, and we have actually been running this in production. So the .id namespace currently has like close to 70,000 registrations on it, right? So all the different experiences of running this network for more than 2 years, we've been iterating over our design and been evolving it. And I can share more details offline for how what are some of the lessons that we've learned and changes we have made in this architecture over time. So let's say that all of this is up and running. What that really gives you now is that you are basically running BlockStack on a device. That device could be your laptop itself, right? It actually doesn't take that much memory and disk space. Like I think the last measurements are, it requires around like 200 MB of RAM, 4 gigabytes of disk space. But you do need a full Bitcoin node as well, and that actually takes a lot more disk space. So let's say maybe you're running it on your laptop, or you're running it on a server that you own, or somewhere in the cloud. Or I think the best solution is actually these specialized devices like a Bitseed or a 21 computer that has a Bitcoin node running on it, and you can also run BlockStack there. And let's say you open your laptop, and your laptop connects to this security box, right? A device like Bitseed, if you buy it and you just plug it in the wall and give it a Wi-Fi connection, it will boot up, it will process, it will download the Bitcoin blockchain. And if you're running BlockStack on it, BlockStack would process all of the transactions and build this global view of the DNS and PKI and storage systems, right? So you're only trusting your box, and that's it. You don't need to trust any other computer in the world. And if you're talking to your friend is only trusting their own BlockStack node, wherever that is deployed, maybe in their room, maybe in the cloud somewhere. So this is what the security on this new internet basically boils down to. You only trust your own device, and that's it. Another interesting thing is that let's say you're traveling. So we have this thing called a consensus hash, which is basically a hash of the global state of the system at any given block. So think of time as moving forward as clock ticks when new blocks come in the blockchain. And we have a consensus hash whenever time moves forward, right? So let's say you're traveling and you're in an internet cafe somewhere in the middle of nowhere, and you want to make sure that, and you don't have time to like process the blockchain from beginning and like construct the latest consensus hash. You can actually just check with your friends that, hey, what's the consensus hash you're seeing right now, right? And then you're like, okay, it looks like I'm on the correct secure network because my consensus hash matches with you. Similarly, for example, organizations like Princeton University or Microsoft is actually planning to run these public servers. So you can actually very quickly check the consensus, just like Google runs like 8.8.8.8, which is a public DNS server that anyone can connect to. Similarly, organizations like Microsoft are in the process of running public servers for this internet, for basically BlockStack nodes. And you can just like very quickly check with Microsoft or Princeton or like some other university that, hey, what's the consensus hash right now? And that gives you an added security that looks like other people are on the same network as me. So so far, I was talking about how BlockStack itself is built, like what is the architecture and how we have built this network. But for most developers, the exciting part is like not how BlockStack does networking or systems architecture, but how can I actually use it, right? How can I just like start building applications or websites on top of BlockStack? So I'm not planning to go too much into it in this talk, but I'll just give you a brief preview, and then you can follow up on the website. or join our community to learn more. So basically, what happens in this new model is that most of the computation actually gets pushed to the client side, which means that you're, by the way, for writing applications on BlockStack, you're just working in pure JavaScript, right? You don't have to learn a new language or a dialect of a familiar language. It's just pure JavaScript single-page apps, right? So let's say you want to make a very simple to-do list app. You just like write the code, sign the code, get a domain like todolist.app, and publish your code there, right? And a user using a browser would go to todolist.app, fetch the code, check that it's the correct code because we know what is the public key that owns todolist.app. And then most of the computation actually happens client side, right? There's very little server side infrastructure that developers now need to manage because users have their own usernames and identity, right? So you don't need to run a database for managing usernames and user information. Users would just bring their own identity and log into the app using like Muneeb.id, right? So we'll have a very basic, JavaScript library that lets users, so developers can just use the library and say, hey, yeah, here's the login button, and authentication and login is just like handled for you, right? Similarly, you don't need to store a lot of data on users because all the users, they have their own data buckets, right? Like they have connected, let's say I've connected my Dropbox or my S3 to Muneeb.id. And the way apps are built is that you're writing data back to the user or back to their data bucket. So if I start using this to-do list app, the data for that will be stored on my Dropbox, encrypted in this special way, so even Dropbox wouldn't know what is that data that is being stored there. And the developer doesn't need to store that data on behalf of the user, right? So building applications in this model actually becomes much simpler than building applications in the traditional client-server way that we are used to, and then we have to manage a lot of infrastructure as developers. I'm not going into too much details on this, but you can basically check out our website. I wanted to go over just the project status because we are open source community, and I think it's great to get like more developers involved with the process. So you can just go to github.com/BlockStack. You'll see most of our important repositories are pinned at the top page. BlockStack Core is what handles most of the functionality. You can actually, this is the old screenshot. The browser is now also available there if you want to just go and check it out. All of our other documentation is just on the main BlockStack/BlockStack repository, and I encourage everyone to go there and check it out. We have launched like several components for BlockStack over the years. The first thing was this registrar. So think of this as like the GoDaddy for the new internet, which is called OneName, right? So OneName is a very simple web app. What that does is that from a traditional browser, so think of that as like a GoDaddy, but it's registering people on the .id namespace on the new internet, right? So that's live. If you want to just go and register your username and profile, you can use this registrar. But even better, you should actually download the BlockStack command line interface, right? So the CLI is basically something you can run yourself, right? So you're not going through a registrar to register your something like Muneeb.id, but you're actually doing it yourself directly on the system, right? And I think as a developer, like that's like way better because you're not depending on this middleman, the registrar. And I mentioned the browser earlier as well, that you can request access to it. It's still in developer alpha. So we still haven't like fully released it, but we are happy to give people early access. So if you download the CLI, maybe you can try that right now as well. If you have pip install, basically pip install BlockStack. You can actually do many things like just do a lookup or do a whois. You can do BlockStack whois, Werner.id, and you'll see the whois entry for him. So this is the sample for Fred Wilson, that it's actually displaying data for Fred Wilson. And you can actually, with the BlockStack CLI tool, you can like register your own name. There's a wallet that actually manages your private keys and spends. So you'll have to send some Bitcoin to your wallet and then do the registration. There are already a bunch of different organizations, both like small startups and open source communities like Open Bazaar, all the way to academic institutions like Open Cloud. Open Cloud is basically, they work very closely with universities, and they provide a lot of services on like next generation storage systems or next generation networking, things like OpenFlow. And so they're actually using BlockStack, all the way to big companies like Microsoft that are using BlockStack. They're actually like, I think recently I heard that they're actually hiring engineers to actually work on open source technology, and have a bunch of plans that I can talk about later on. So I mentioned that, so this number is outdated. The registration in the .id namespace are now close to 70,000, I think. And just like I'm here presenting remotely at the meetup, we have been going around the world, or people have been organizing meetups around the technology. Again, I think this screenshot is outdated. I think we have more than 4,000 members worldwide now in our meetups. And we would actually love to have more meetups in North Carolina. So I don't know if James or anyone else is interested. I would love to like talk more about that as well. Obviously, this is not just my work. I'm just one person. This is some of the core team. Ryan Shea, my co-founder, and then we have Jude and Guy. And we have some links to the distributed systems community in the research and academia as well. So two of the professors at Princeton University are actually advisors, and they've actually co-authored papers with us, and we've gotten them peer-reviewed and published in traditional top-tier computer science conferences. And I personally feel that that's very important, because when looking at this like blockchain area, everything is not new. Like distributed systems have been around for 30 years, right? So a lot of stuff that we are building, or roadblocks that we are hitting, people have looked at these things in different contexts earlier, right? So I feel like it's actually very important for the blockchain community to engage with the traditional crypto researchers or the traditional distributed systems researchers. And it will not only help to build like better, more secure, more robust, better scalability systems, but it will actually also help with introducing them to the technology. And there are some of the best minds out there who have like thought about these problems for decades, and that can help the ecosystem a lot. So we have done our part. We have actually published 3 papers now in some of these like traditional top tier computer science venues, and I encourage you to check them out. You can go to blockstack.org/papers, and you can see a list of the published material. So looking at the big picture, like one interesting thing that's happening is that if you look at the internet, the core protocols like TCP/IP or HTTP, they were all open source, meant to like build an open network, and the people who are actually working on these protocols, they monetize things a little bit, but probably not a lot. Nothing compared to what happened at the application layer. So I put Google or Facebook in the app layer. They were enabled by the internet stack, and they ended up capturing all of the value, right? And think of it this way, that now the Googles and the Facebooks of the world have all the resources to go and hire engineers, give them incentives. Like, for example, a Google engineer would get stock in Google and a good salary to now go and innovate on top, right? And interestingly, these companies actually had to go back and innovate at the infrastructure layer as well. Like, Google has built new protocols that make HTTP requests faster, or Google has built like these data stores that are like extremely scalable, and they belong in the infrastructure layer. And sometimes they open source those technologies as well, but most of the time it's basically sitting within Google, right? If you look at the decentralized internet, so what's happening is that it's completely possible that you will get on the right side, you will get a more thick infrastructure layer, right? Because now you have this concept of a protocol token that is almost like a shared value of the ecosystem, right? So instead of a developer having, because this is not a company, it's a protocol. Just like Bitcoin has now I think a 16 billion market cap, but Bitcoin is not a company. Bitcoin is a protocol, and there are multiple companies and multiple open source developers who are kind of like quote unquote shareholders of the success of that protocol, right? Similarly, in a new internet, you can imagine that there is this shared token that represents the use of that network, right? So you are actually, and right now in BlockStack, that token is Bitcoin. So you're actually burning Bitcoin and to register names, right? But this changes dynamics a lot, right? Because it gives engineers the incentive to just hack on the infrastructure itself and grow with the ecosystem, right? And then later on, you can build decentralized applications on top, which obviously will have like some sort of a business model or a monetization policy, but it will be much harder for those applications to become really large monopolies like Facebook or Google, because they're able to become these monopolies because they control all of the data. Facebook has data on basically everyone, right? And they would not let other developers use that data because that's the gold that they're sitting on. And in the decentralized world, that's not going to happen. So in general, I'll just leave you with one last thought, that in the real world, we have property rights. If you look at the online world, we never really figured out property rights online. We were kind of like renting spaces from companies like Facebook and just putting all of our belongings there, right? With blockchains and with stacks like BlockStack, now you actually have the functionality to own things digitally online for the first time, right? With Bitcoin, you can own money. With BlockStack, you can actually own your username and your data. And when app developers start building apps there, again, it's like those developers own these apps, right? No one can like just shut down an app or take it down, remove it from an Apple App Store, for example, right? So this concept of like bringing strong property rights to the internet, is something that is extremely exciting for us, and that's what keeps us going. So on this new internet, I can own Muneeb.id, or Werner Vogels can own Werner.id, and we can have this like little space for ourselves. It's kind of like buying a piece of land and building your home there and putting all of your stuff inside it. I can actually buy this piece of digital land and put all of my data, all of my belongings, all of my digital life in there, in a place that is owned by just me and not anyone else. So the old internet basically asked us to blindly trust and didn't give us ownership of our data, but the new internet can actually fix that, right? So with that, let's open it up to questions, and let's go and build a truly open and fair internet.
All right. Awesome. Thanks. So I'm sure we've got a number of questions. Let me start out with some of my own. Now, if I recall correctly, weren't you originally using the Namecoin blockchain to anchor into?
Yes.
And I was wondering if you could speak a little bit about why you decided to move away from Namecoin.
Yeah, absolutely. So for people who don't know what Namecoin is, so this is, I think, Ryan and I started late 2013 to start working on this. And at that time, we were basically evaluating that should we build this on top of Bitcoin? Even at that time, it was by far the biggest blockchain and most secure. Or should we go for a solution like Namecoin, which forked Bitcoin and added some of the functionality that we will need to add as well? More specifically, it added the ability to register names and store like very small amount of data right in the blockchain. They were putting data in the blockchain itself. And the third option was that should we just build a new blockchain and design it however we want to, and take that approach. So after like much back and forth, we basically decided that Namecoin is the fastest route to deploying this and going live, right? Because they've already done a bunch of work that we need to do. And if need be, later on, and we were concerned at that point with some of the security implications of being on a smaller blockchain or using a blockchain that is not that actively maintained and stuff like that. But we thought that maybe we will become the developers there and start helping the community and take it from there. So fast forward, we used Namecoin for, I would say, a year and a half. We were probably the largest system that was running on Namecoin. I think there's an analysis done by Arvind, his professor, and students that they compare usage of Namecoin and stuff like that. And what we learned was, like, one of the biggest things that happened is a single miner had more than 51% mining power on Namecoin. Right? So blockchains are decentralized as long as no single party has more than 51% of the mining power. I mean, not like all hell breaks loose if someone has that much power, but there are certain types of attacks that the miner can do. And obviously, if that would happen on Bitcoin, people would be screaming, right? And that has happened where the Bitcoin community would actually react and they would leave that mining pool and try to do something about it. But in Namecoin, the scariest thing was not that a single miner had that much power. The scariest thing was no one noticed. We were the only ones that actually noticed that thing or were studying it. And so we silently started working on an implementation that is agnostic of any blockchain, and that can actually work on any blockchain. But there were other things as well where, for example, the network wasn't as reliable. Like in one instant, what happened was, so imagine that the analogy here is that everyone that is building applications and services on the internet is using the same underlying pipes, right? So if something goes wrong, a lot of people notice, and then people react. So there's more incentive, more economic incentive to keep the underlying infrastructure running, right? So with Bitcoin, the largest blockchain, there are lots of companies, lots of people running live services on top of that. So a lot of people are actually watching the network, right? Or their businesses are linked to the uptime of the underlying network. But if you're on a very small blockchain and something goes wrong, but no one is really impacted by that, there's less incentive to fix those things. So we noticed stuff like, there was a bug in the Namecoin software that was triggered by someone sending transactions with a large amount of outputs, and then miners were crashing and they were not processing transactions, right? So for like 3 weeks, we actually did a study of this, and it's in one of our papers where we actually plot and show like what's the normal throughput of the network and what happened in those 3 weeks, right? Like so instead of like getting a transaction through every 10 to 40 minutes, you were actually waiting a much longer time. So that was one thing. But in general, our takeaway was that blockchains are in a, and this is very interesting, that blockchains become more secure the larger the network and the more people kind of like using it and have economic incentives to grow the network. But when they're small, let's say you're starting a new blockchain, they are the weakest at that time, right? So blockchains kind of like have to go through this process where when you're starting it, it's like very weak and small, and someone can take over the blockchain by throwing a lot of mining power at it, or the software is not that stable, and so on and so forth. But once blockchains become really mature, let's say the Bitcoin blockchain, it becomes that much harder to change it, right? So there's like this strange trade-off that they're not secure when they're small and easier to change, or like I can just start a new blockchain and add some functionality. But once they are secure and they're stable and they're reliable, it becomes very hard to change them, right?
Definitely.
So
that has a lot to say about the network effect and probably open source communities in general. The larger the community, the more you're going to be able to find problems and solve them.
Yeah, absolutely. So what we kind of like took away from that is that we should really think of this as like decoupling the layers on top from the underlying blockchain, right? And always be on the most secure blockchain, but we cannot expect let's say the Bitcoin developers to change the Bitcoin network to suit our needs, right? We have to design our system in a way that it can just like run on top without requiring any support from the underlying blockchain. So the system that we have designed, it basically has this one property that the underlying blockchain needs to be able to give you total ordering of all operations, meaning something very simple, that it should be able to tell that operation A happened before operation B, right? And all blockchains have that property, right? So as long as we can write data to a blockchain and get total ordering of operations, we can actually run BlockStack on top.
Sounds good. Any questions? We've got a few dozen people here. I'm sure we've got a few curious people. Here, let me walk over to you with the microphone so that Muneeb can hear you. Here you go.
All right. So with the block stacks that people are running, what if you have a corrupted block stack communicating? Is that immediately kicked out, or what type of security is being prevented from something coming in and corrupting it all?
Yeah, absolutely. So imagine that you start a BlockStack node. Either you're trying to be malicious, or for some reason there is the bug that is triggered just on your deployment, and you end up constructing a different view of the network, right? So you cannot impact anyone else. Only the people who are trying to use that node that is faulty will be impacted, right? And a very easy way around it is that these nodes are supposed to check with their peers that, am I on the same consensus hash or not, right? So a faulty node can even detect that, hey, none of my peers are on this consensus hash, something is going wrong, right? And you can then try to do something about it.
Other questions? Raise your hands. All right. It's pretty sensitive. You can just speak more.
I have kind of more of an abstract question. So I can kind of see how you have a digital property that's kind of your own Werner ID, so to speak. But what about like your digital content that that you create? So say for instance, Werner posts something on BlockStack browser or something like that, and you have the concept of a share. Is there a way for people within the community to say, oh, well, this share is original content from Werner? Is there some type of trust type of thing that could be envisioned that would work off of BlockStack or something?
Yeah, absolutely. So, first of all, I would say that the problem you're trying to solve is actually more complex, because it's kind of like about digital copyrights in a way, right? That, hey, because it's so easy to just copy files. Let's say someone creates a piece of art, and then someone else shares it, and then someone else, like 1,000 people share it, and now it cannot be attributed back to the original person, right? So I think it's a more complex, higher level problem that we have with digital content. And there are, you should look up this company called, their open source project as well, called Media Chain. And they are targeting that specific problem. And they have certain ways of dealing with it where they try to create, let's say, some sort of a fingerprint of a piece of art or that digital content, just to uniquely identify. And then people build like some sort of reputation scores, and the community tries to ascribe that this content was actually originally created by that person, right? So obviously it's not a perfect solution, and they're actively working on improving it. But I would say that they've probably thought about this problem more than a lot of people.
Cool. So I've got all sorts of questions, but I'll pick one, starting with your premise, which is the original tools for dealing with the old internet are broken, and we need a new set of tools. I guess the one question people would ask is, why don't we fix the current set of problems with the old internet and keep it running? Mm-hmm. You mentioned the DNS is being a point of attack, and that most people trust their internet provider's DNS. There's plenty of open DNS and Google DNSs and other DNS targets that you could go to for top-level information and get your names in a more authentic way. But I still don't see, I see non-repudiation in the blockchain. I don't see authentication. I don't see some accreditation of the data in the blockchain, and I don't know how you're putting that into your BlockStack. So that I think you've got a whole set of new problems in the new internet as well.
Yeah, cool. So I think there are several parts to this, and I'll try to address them. First of all, at a very high architecture level, so David Clark at MIT, he was the chief protocol architect of the internet in the 80s, I think for roughly 10 years. And he led like most of the development of currently what we know as the internet. And I was having a discussion with him about this, and he actually gave a talk where he was reflecting back on the design decisions that they made. And there's this famous principle called the end-to-end design principle by David Clark, which basically says that you shouldn't leave complexity inside the network. Complexity should be handled at the edges, which is what happens in the internet. You know, it's a dumb network. It just delivers packets from A to B, and then we keep all the computations and complexity at the edges. So looking back, he said that the one thing that they should have done with the design of the internet is that they should not have left these trust points in the middle of the network, meaning that the internet should have been designed in a way that the trust was also completely end-to-end. You don't need to trust anything in the middle of the network. And so he now has a new design principle called the trust-to-trust design principle, which, like, in a way, what I'm saying is the original architect of the internet thinks that the trust-to-trust design principle is what should be done with any modifications that we do to the current internet or any new internet that we build, right? So that's just the high-level architecture part of it. The second thing about fixing the current internet, like, I think the analogy is kind of like the New York subway system. Like, once it's built, like, it's like very hard to fix it. And it's not like there aren't efforts to fix the current system. There are, and we are engaging with those people as well. We are actually talking with ICANN for a top-level TLD for BlockStack, in a way that we're saying that here's an alternative route, and if ICANN can start supporting something like .blockstack, like, that's one way for our system to integrate with the existing system and so on and so forth. But DNS, like, there have been several attempts to fix DNS, but it's not just DNS, right? It's also PKI. It's also how where data is stored. So like you can look at, like, for example, DNSSEC, and we are in touch with the inventor of DNSSEC, and he's helping us think through this process. That in DNS in general, there is basically a hierarchy for your query, right? And you can try to establish like some sort of authenticity that you're getting the right results back. In BlockStack, there's no hierarchy. There's just one server, and you connect to it, and you have the cryptographic mathematical guarantees that you're actually getting the right results back, right? So in a way, it's actually a very simple solution. So instead of like putting more duct tape on an already broken system, what we're saying is that here's an alternative that is actually much simpler if people want to start using that instead. And that's just like the DNS part. Now moving on to the other part, which is PKI. And so again, there are efforts like, let's say, Let's Encrypt, like great project. They're giving everyone these security certificates for free, which should have been free all along. Like everyone should have these certificates on by default, right? Not that, hey, you have to go and purchase a security certificate and then put it on your website. Right, so Let's Encrypt is trying to kind of like fix the existing internet. What we are saying is that by default, all domain names are owned by public keys, which means that there is no possibility that you can have a domain name or a username or anything that does not have a public key, right? So again, I think it's like much easier to do if you bake that into the new system, right? Where now security is on by default, right? Even with Let's Encrypt, you have to go and like, remember to get a certificate, and then most people still don't have it. So I think when you start designing something from scratch, there are certain advantages where you can just bake things into the design and just like help everyone just upgrade by default. And obviously the challenge is that you're trying to build something new. So how adoption works for that. And I think that's where I tried going over the control plane and data plane analogy, that I'm not saying just throw away the entire internet. I'm saying that we need to establish a new control plane that we can use for authenticity of things. And we can use the existing internet infrastructure, the existing protocols, TCP/IP, all the pipes, everything that we have done in the last 30 years for data delivery, and just don't trust that data that is being pushed through these pipes, right? So the last part about revocation, we actually do support revocation in BlockStack. I would say that what we have currently is no worse than how revocation works in the existing system. So I would push back a little on that, hey, we are introducing new problems. I would say that the system that we have is no worse than the existing systems in certain aspects, but in a lot of other aspects, we're actually improving a lot on what's available. Any other questions?
All right.
Just one other quick question. Like, so, really excited about it. So when we leave here tonight, what could be like a next step for us or whatever in terms of interacting with BlockStack?
Yeah, that's a great question. So we are an open source community. I think we have around, we use Slack as like the live chat channel, but we have a forum. So just go to blockstack.org and try joining the community, right? Like it's, all the development is done in the open. There are outstanding issues on GitHub. It's not just like things for developers to do, but also we are looking for a lot of help in telling more people about the technology, or in marketing, or in design. So like basically go to blockstack.org and you'll find links to get involved. And again, like this is a project where developers are building this technology for other developers in an open source way, and we cannot do it without involving more people.
What about your scaling of your network? Let's say this takes off very rapidly. All of a sudden, you're getting much larger data packs, or bigger chains. Also, is the chain immutable, or is it, let's say you want to take something off that you put on that you really didn't want to put out there? What about those two things?
Yeah, and I kind of had a similar point to make of, I was looking at end of year blockchain usage stats and like op return protocols, and I believe BlockStack was in the top 3. And I know you're blockchain agnostic. I'm wondering if you're seeing any issues with the contention for block space and increasing fees on Bitcoin, like how that is affecting people using BlockStack and what blockchains they're choosing to anchor into.
Yeah, absolutely. They're great questions. I will again divide them into different parts and try to answer them. So the first thing about scalability is going back to the separation of the control plane and the data plane. Where blockchains come in, we are only concerned about the initial registration, right? We actually redesigned. So imagine I'm registering Muneeb.id for the first time. That's when I hit the blockchain, right? And in an earlier version, if I need to update like my data mappings, I actually had to send a new transaction, but I no longer need to do that. So most of the stuff is happening in the data plane. If I'm updating my bio, or if I started using a new app, or any activity that I'm doing is not hitting the blockchain. The only time I need to hit the blockchain is basically if I'm updating my zone file, which is the equivalent of you saying that I am changing my provider, and I want CNN.com to no longer point to this, but I want it to. I'm moving my server somewhere else, right? So things that you do very infrequently, you would be hitting the blockchain. So that's the first part, that we are only concerned about giving every human or every app like one identity, or let's say a couple of identities on this new system where we will hit the blockchain, right? So it's a much smaller problem than running everything on the blockchain or putting all that data there. And that gets into the question I had earlier about like, if you put data there, will it stay there? The answer is the data that you do put in the blockchain will stay there. But that data is actually not very meaningful about what you were trying to do or who you are, right? Like if it would basically, the data is that this public key owned Muneeb.id between 2015 and 2016, right? And that's about it. They don't know this is actually me. They don't have any data on my profile or my verifications or my applications or anything else, right? It's just like one human readable thing with a lot of garbage that will be in the blockchain. Everything else is outside, and there's no permanent record of that. Now, going back to scalability, there are a bunch of solutions that we are working on for scalability. We absolutely realize that if 1 billion people start using this, and which is actually not that far-fetched, because Microsoft recently announced that they are working on the technology, and when we were having discussions with them, one of their requirements was that what if we want to move everyone who has a Microsoft Outlook account, for example, roughly 1 billion people, to this system. So like this could happen like sooner than we think. Obviously, we're not going to send 1 billion transactions on the Bitcoin blockchain to get that done. So the solutions that we have in the pipeline, one is using the subdomain-like system, right? So now you are not registering muneebali.com. You are registering something like an email address, like Muneeb at some provider dot something, right? And that we can actually scale to billions of users without hitting the blockchain. right? So, and if you look at traditionally, only power users on the internet would have their own .com, right? Like most people just have an email address or an account somewhere else. And even with this system, the security guarantees are almost the same. And I'm saying almost, that basically, like visually, the name looks a little different, right? And let's say the owner of there's, let's say, something similar to Gmail. Let's say there's like gmail.id, and I want to get Muneeb at gmail.id, right? Whoever owns gmail.id cannot do anything to my entry and my registration once it's been registered. So after that, my Muneeb at gmail.id is registered, it's exactly, the security guarantees are exactly the same as if I registered Muneeb.id, right? But the scalability is like, we can take this thing to 1 billion, right? And I can get into more details on what the current proposal is and how we're thinking about that. So that's one thing, subdomains, right? You think of that as subdomains or email addresses. The second thing is support for multiple blockchains. If you look at the internet, the .uk TLD is managed by the United Kingdom. Similarly, BlockStack has this global namespace that has information on the namespaces itself, which, by the way, reminds me that a really cool thing about BlockStack is that you don't need permission from ICANN to start new namespaces. You can just download BlockStack, and if you want to start, I don't know, let's say git for GitHub, you can just go ahead and start that namespace.
That sounds like anarchy.
Yeah. So and it's all programmable, right? So you can actually set the pricing rules, that how domains can be registered. You can mess around with a lot of settings. It's really fun, and you don't need permission from ICANN or anyone else. So let's say that that information on the namespaces itself lives on the Bitcoin blockchain, but the actual namespaces can actually live on other blockchains. So think of this as pointers, right? So let's say I started a namespace .linux, but I specified that this actually lives on the Ethereum blockchain or the Hyperledger chain or some other blockchain, right? So the amount of information that is being stored on the Bitcoin blockchain is actually very little. Now we have to worry about the scalability of the .linux namespace on that blockchain that is actually hosting it, right? And in the future, you can actually imagine other types of sidechains or blockchains coming out that have like that they make other design decisions, where let's say it's like highly imagine like a data chain, right? That it's not as decentralized as Bitcoin, but it actually gives you faster writes, higher throughput, and it's like federated or something like that, right? And then I can have a namespace living on that blockchain where people understand the trade-off that they're making by using that namespace. So that's another thing that we are looking into, basically supporting multiple blockchains and then following pointers to those blockchains.
Any other questions? All right. I know that you spoke about the different storage solutions that you're supporting and how the decentralized storage solutions have their own slew of problems. So have you actually experimented with trying to use something like Storj as the storage layer? Can you speak about what
we haven't specifically with Storj. We do have plans to integrate IPFS as the first one, and we are happy to talk to the Storj people as well for writing a driver. But when I was saying that about decentralized systems, it was more of like the scars that the earlier generation of P2P researchers got, and our experience has only been with deploying. We were running a distributed hash table based storage network for storing all the routing files. So this is actually last year, where every BlockStack node was also part of this storage network where the zone files were being stored. And if you think about it, those zone files were actually very small, and theoretically, we shouldn't have any problem like storing that amount of information in a decentralized storage system based on distributed hash tables. And I can share details on like what were the performance issues that we experienced, what were the different networking problems that we ran into, where let's say the nodes in Hong Kong were actually out of sync. So someone is trying to actually update their profile in California. I'm seeing it in New York, but the person in Hong Kong is actually not seeing it. Then there were stuff with churn where someone, let's say, turns on the BlockStack node. They actually don't mean to leave it running online all the time, but they join the network, and then they start storing a bunch of data, and then they leave the network, and now the network has to reconfigure itself because that node is gone, right? So if a lot of churn is happening, that we started seeing that when there were more nodes, the network was like constantly basically trying to resync and balance the fact that this node is gone. And so these are problems which are common in most decentralized storage systems. And so my comment was not on the new generation systems like IPFS, Storj, and others. It was more on the fundamental underlying design that is, I believe, common to most of them. And the lessons are more about people who tried doing it like 10 years ago, kept banging their head on it for 5-6 years, and then in the end wrote some paper with all the things that went wrong, right? So I think we should pay attention to that institutional knowledge when designing our systems.
All right, awesome. I think we've about dried up all of the questions. So I think thank you very much, Muneeb, for joining us and sharing your wisdom and insights and your vision. And we're very excited to see where BlockStack goes. And it seems like there's a great deal of potential, and I would definitely wish you the best in your endeavors.
Yeah, thanks for having me. This is great. And hopefully we can do one in person sometime.
Yeah, definitely. Well, signing off for now. I'll see you soon.
All right.
Bye.
Take care, Rick.